Good afternoon. So today we're going to be doing sweep frequency response analysis, excuse me, session three. And as it turns out, this is going to be the last session that we're going to do on sweep frequency response. I was going to actually hook up the equipment, but I'm out of state, so I'm not going to be able to. So today we're going to talk about traces, normal traces, abnormal traces. Uh, don't know exactly how long it'll take, but we'll go through what I'm aware of and the best I can try to explain these things. So when we talk about sweep frequency response, we're going to have normal and abnormal traces. And if we're going to talk about the various plots that we're going to see, remember that it was 20 log, base 10, V out over VN, and we're always going to have a reduction. So we're going to have a loss in dB or decibels. And so this magnitude plot of the signal reduction through a piece of the equipment. So it's always going to be reduction. We're not an amplifier here. The x-axis, going across is going to be the frequency in hertz. Okay, and then the y-axis is going to be the decibels, the actual loss. I guess I should have done dB like this. Actual losses on that system, okay? The ratio of output to input losses. Typically, the frequency will be on a log scale. So it'll look a little different. It's like, so 1, 2, 3 will be far apart, but as you get closer to 10, it's getting smaller and smaller. So we'll actually review that. But we're going to be looking at the magnitude, and we're going to be looking at the frequency of these plots. Now, what we're actually seeing here, and this is the high voltage open circuit, HVOC, high voltage open circuit of a delta Y transformer, and we're looking at the delta side. Again, as we mentioned before, every time I see a peak, every time I see a point, that is a resonant point that we're looking at, okay? And when we see the delta side, when we're looking at a delta side and we're looking at open circuit, we're actually going to see this double dip at the bottom for that. And so I'm going to be looking at two waveforms. These two, there are actually two of them there that are right on top of each other. I can see a little bit of orange or magenta here. It's supposed to be red, but it's mixed with green, so it looks looks the same. Two of them are going to be exactly on top of each other, and we can see that. And we see the typical third phase, the blue phase here. It's always off a little bit. And that's because that is the center phase. It's wound between the other two windings. I might not see as strong of a dip for the second dip, but it's going to be in there. So two of the phases I can compare very clearly because the two outside phases should be pretty close. I see a little variance here, but not much. The big deal is the resonant frequencies are basically the same on both of those two phases. There may be a little dip. Now they get really close together, the remaining out, so they're pretty close and pretty tight there. So that would be a pretty typical response to that delta open circuit test. Now, again, we look up in here, we see some variances, but we've got to remember that that's the high side connections, and that's the bushings coming out of the transformer at the higher frequencies. And so there's going to be different lead links there going to different bushings. Each bushing is going to be a little different with a little different resistance. So I can see that there could be some variance when I get to that high frequency end. But down here at the low frequency end, I should be very consistent, at least with two phases on that diagram. Now, when I look at the regions of influence, okay, I'm sorry, looking at the diagram here. This is the low voltage winding, okay? So this is the open circuit test for the Y winding. Again, I don't see I see a V here, okay? And a little bit of but everything is really tight on these resonant points here. But again, I see a typical center phase variation, one by itself. The other two are right on top of each other. Again, the only variance I see is up toward the high frequency end, which are the connections and the bushings themselves. So looking back, I can see the wide kind of a box thing there for the delta winding, and I see a really sharp V or a very sharp W right here for the Y winding. So those are pretty typical responses. Again, the biggest thing is I want to be able to compare them to historical data, historical test on this same transformer, but I don't always have that, especially for the first time where you got a customer who just had a fault and he's never had the test done before. So if we look at typical regions, okay, this is typical, okay. Uh, what are the areas of influence? So region 1 is less than 2 kilohertz, okay? If I see problems in that region 1, basically that's core issues, okay? Uh, Now, it could be open circuits, but open circuits would have shown up on some other tests as well. Could be shorted turns, but that would have shown up on my TTR likely. But big thing here, it could be residual magnetism. So core issues, residual magnetism. Those are the two big things I'm looking at for this low frequency, less than 2 kilohertz. Now, when I look at the area between 2 kilohertz and 20 kilohertz, that's the interaction that I have between the two windings or between the three windings. So let's look back here from 2 kilohertz to 20 kilohertz. Here's 2, and right here is 20. So that's the area that I would be looking at on this Y transformer. 2 to 20, that would be here to here on the delta transformer. That would be the area that I'd be looking at, and that's the interaction between the windings. And I can see a lot of those interaction between those windings, especially on the delta winding. Part of that's in there, that I see the little comparison between the two, the various windings. Then up from 20 kilohertz to 800 kilohertz, that's deformation, okay, within the main or a tap winding. So that's actually deformation of the winding itself. And then when I get up to this higher end, the 800 kilohertz to 2 megahertz, again, that's winding leads, that's winding bushings, that's grounding issues over there. So that's an area where I can expect to see some variation because, again, I've got different lead lengths, different bushings, those sorts of things. So let's look at the high voltage short circuit tests. Okay, so we've done. We're always going to do 6 for a 2-winding transformer. We're always going to do 6 open circuit tests on the high side and the low side, 3 on each one, and then we're going to do a short circuit test where on the high side we apply the input signal, on the low side we tie everything back together like X1 to X2 to X3 back to X1, leaving the neutral or XO open there. So we're going to look at the high voltage winding without the influence of the core. So we've taken the core out of the fact because it's short circuited there on the secondary side. The magnetic circuit of the transformer influences the low frequency range. So short out to secondary winding eliminates the influence of the core. So basically this test, good test on a NETA 3, NETA level 4 exam, this high voltage short circuit test is very similar or a test that's very similar to the leakage reactance test that we can run with our Doble test set. So if I look at this high voltage short circuit analysis, I'm going to see some things here, okay? But I'm looking up here at this section between 100 hertz and 1 kilohertz. So in this slide, I'm looking between here and here. Now, if you notice, I went back here. That's the area of core issues or residual magnetism. So but on the short circuit test, I've taken out the impact of the core itself, the influence of it. So basically, I've taken out the influence and I'm looking at the core. This should be right on top of each other, even to the point where we will expand that and we'll make it large, and that's one of the functions you'll have on your SFRA test set, looking at the results, is to see that expanded for that section of 100 hertz to 1 kilohertz. And I want to basically see, I want to see a straight line. I want to see them laying right on top of each other. And if I see a variance of dB or greater than 0.2 dB, that might be reason for a little concern. So if I look at this one, these two guys look really close. This third one down here looks like it's out of line because it's 25.5 to 25 point something. So it may be within 2, but it's one winding right there is a little different than the other two. That area should be right on top of each other, and that's what you're going to look at on that high voltage short circuit test. Not so much here. We can do some comparison with previous results, but we're not looking right there so much as we are from this 100 hertz to 1 kilohertz range to see if there's a problem. So that's analysis that you have to do yourself outside of what the software will do for you. So causes of a poor test with result to the core itself. You can have the core to be magnetized. That still may be a valid test, but I just can't compare it to other tests. The core ground hasn't been installed or has been removed, okay? So that could be a concern. Shorted turns. No oil. Again, I can run the test with no oil, but it's not going to compare on the short circuit on the test. Poor shorting leads. Okay. On that short circuit test, if I haven't looped from X1 to X2 to X3, looped, and then back, if there's a problem with any of those leads, that's going to be an issue. And also the initial review, factory to field. There can be some variance there because in the factory, they may or may not have had oil in it. I don't know. When they ran the test in the factory, they had their bushings in it and not the ones that shipped with it. So there could be some variation there. So there's some results that I might get from the factory that may not match up exactly with what I see in the field the first time I run the test. Now, let's look at a situation with the core magnetized. Okay, so these are to be some various ones. Look at the core response in the low frequency area, okay? If I see a huge variation, then that would be an issue that I would have, okay? So this is H3 to H1 and H3 to H1. So this can be two different tests on the same winding, and I can see that there's a huge difference at the low frequency for magnetized core. So if I'm seeing a lot of disparity between my historical data on those low frequencies up to about a kilohertz, then that can be a core magnetization, especially if it looks linear. It has the same shape as the other, but they're just separated. Again, that's the same winding, just one's magnetized, one's not. Core magnetized. It's only going to impact the low frequency. If you have a magnetized core, the test is still valid for everything better than 2 megahertz or 2 kilohertz. I'm sorry. It doesn't negate the results, but you got to pay attention to the low frequency results. It can change, okay? If it's necessary, you can demag the transformer and retest, and that's what they've done on this one. They've demagged and got to retest. It can be confirmed by comparing excitation tests. We've already done the excitation test prior to their SFRA. That's the way we do things. If I got a bad excitation test, it could have been because it was magnetized core. Hopefully, I've already corrected it there and demagged the core and run an excitation test, so I don't have the issue when I get to the SFRA. What about an ungrounded core? Okay. Well, I can see a difference here. Again, it's going to depend a lot on my previous historical data. I can see that, the white is the ungrounded and the orangish color is the grounded. This is what I would have seen before. That's my history. But if I'm running some tests and I've done my installation resistance on the core ground to make sure I do have a core ground and I haven't tied it back down, I can see this. Notice different frequency response. One of the things I'm looking for between data is I may see a little variation between the magnitude of two waveforms, but the actual resonant frequency should be right there. And this should be a giveaway. It's like I've got to look at something here because my resonant frequency for that winding has changed. Shorted turns. Okay, we talked earlier that that high voltage open circuit test, Uh, Here we go. Phase A is shorted. Look at the difference between phase A waveform and the other two waveforms. It's got a linear pattern, and it's got a function here that resembles the direction of this one, but there's so much variation here that something had to happen. So that would be a shorted turn. Again, I would hope that we would have caught that on our TTR or other tests, but this would help to confirm that. It's on the high voltage side. Now on the low voltage side, similar sort of thing. There's phases B and C. Man, they're right there. They're on top of each other. From that 1 hertz to 1 kilohertz, looks like they're probably right there on top of each other. But guess what? I got something way different here at the beginning. Now, I've got some variation down here too as well, but that beginning's a dead giveaway that something's going on. So that would be an indication of a shorted turn on the low voltage side, the open circuit test. With or without oil. We don't typically do the test without oil, but they can do that in the factory. And so that may have been what they've done in the factory. But here we see a difference. Even in some of the resonant frequencies down here, this is without oil. I get higher resonant frequencies. With oil, I got lower resonant frequencies. So I see the double dip, but they've shifted. Again, I see a shift in my resonant frequencies left to right. That's a concern that I have to be able to answer, because even though the magnitude may change, repeated over and over again, that shift of resonant frequency should not change. High voltage short circuit test, but I've got poor leads, poor shorting leads. Doesn't look really bad, but I got some noise right there. I shouldn't see that noise. I see the little humps in back. I mean, it should be a straight line there going down. I see that little variation in the frequencies. That's an indication I've got poor shorting leads going on. Factory test, field test. Factory test, full of oil. Okay, you got there early and did a test in the field without oil. That is you understand why the shift in frequencies, but the waveform looks the same. But look what happened here. I get up to the higher frequencies, which is the connection and the bushings themselves. There's two different kinds of bushings there. The factory put one set in. That's not the set they shipped with the transformer. So I can expect a mess up here. Again, I would want to run this test again after oil was put in to verify that that everything's good there. Now we do have tap changers here. And if we look at that de-energized tap changer, we can see some variation there. I can see, look at the waveform here. This is a high voltage open circuit test on one phase using the de-energized tap changer. Look, the waveform looks exactly the same. I just shift over the frequency. I can see each different tap. No change in the waveform. There will be a change in the resonant frequency because I've got more windings in it, those sorts of things, more turns in it. But if I see some spurious response, if I see something squirrel going on in here, then I know that maybe I got a problem with position E of the tap changer. The waveform should look very similar, just displaced on the resonant frequencies. Here's my low voltage tap changer. The load tap changer where I've got 16 raised, 16 lower. Again, look at the waveforms. They look exactly alike, just displaced on the frequency axis to show different resonant frequencies. Good picture there showing no variation in the waveform, just horizontal displacement for frequency response. Okay, high voltage open circuit. This is the one that we've seen before. We've all done this before. You forgot to take the ground off XO. There's the double dip I'm looking for. I don't see that same double dip right there with the grounded connection. So that would be an indication of that I forgot to take the ground off and let XO float. Poor ground reference. Okay, should be reference instead of referencey. That might be shown up here at the higher frequencies. Again, that would be hard to determine. because that's where I would see garbage because of bushings and lead lengths and those sorts of things. Uh, but if I'm looking at original and I'm doing a follow-up historical review, they should be right on top of each other. So that would be an indication of some grounding issues external. So strategies that we have. We want to compare with reference data. And the best comparison we can have is previous test on the same unit. The second best test is the sister unit. Now, sisters aren't always alike. And the third best test is phase comparison. But remember, that center phase is always going to be different. So this is the one we're going to fight for. That's our selling point to the customer, that we want to make sure that we have multiple tests on this transformer so we can review from the baseline. So now we can have small variations up and down. That can be expected. But resonances, they should stay the same. So x-axis should stay the same. Y-axis, they can be up and down a little bit. Watch for major changes, even in the y-axis, the power, the dB loss. Any new resonant frequencies, any loss of a resonant frequency, those are huge. Or if the resonant frequency has shifted over 2 kilohertz, those are the three areas that we really, really want to look for. New resonance, loss of resonance, or a shift in that resonance of more than 2 kilohertz. That's an indication that we've got to do some more research and to find out what's going on with this unit. Comparison between previous tests. This is a Doble chart, okay? So expect similarity in certain parts of the traces, expect differences in certain parts of the traces, okay? So here is the open circuit test. We have a difference right here in this lower frequency between the previous and the existing, but the core, remember the core is involved there. So the core could be in a different state of magnetism, okay? It may not be magnetized enough to destroy everything, but should have, maybe it's got some magnetization in it, okay? Up here in the higher frequencies, same unit, maybe it's been removed, maybe it's been moved, you got a different grounding system on it. On the short circuit tests, all 6 phases should look alike in one line. Again, remember, area of interest, 100 hertz, 1 kilohertz. They got to be on top of each other. That's what I'm looking for. If I'm comparing with a sister unit, certainly variations can be expected because it's been wound as different transformers. The biggest area of difference would be, or that could happen, is the high frequencies. Again, the high frequencies here, again, those are bushings and those sorts of things. They can be a little different, okay? So we can see an area that they've zoomed in on here. These things look really close to each other between the sister unit and the unit we're testing itself. Sister unit continued. On this short circuit test, I'm looking in this window again, right? And I can see that from one end to the other is only 0.1 dB, and my variation limit was 0.2 dB. So even with the sister units all together, I can feel relatively comfortable that the short circuit test is looking okay. Now, third test, comparisons, phase to phase. This is the one I like the least. I'm looking at phase to phase, okay? Always trust your high voltage short circuit test, okay, and hold that 0.2 dB variance in mind. You can trust that phase to phase. But with the high voltage open circuit, it's tricky. It's very tricky. I'm going to have 2 of them together. I'm assuming that if I've got 2 of them together, this green and the black, they're almost all together. That looks pretty good. Little variation there. The red, I don't know. I don't like the looks of the waveform here, but I don't know. This is my typical delta connection. I would have expected this frequency to be over this way a little bit and over that way a little bit, but different as far as the magnitude. But I can't verify that because I don't have the previous historical data. All right, that pretty much summarizes everything that I know about sweep frequency response analysis. So we're going to end it there. And I just, again, please ask that you send me notice when you have reviewed this video. Thanks and have a great day.